So day 2 of Unit 4 notes, graphing. And this first one, these are all sort of like parent functions. So we're going to just old school table of values these and see what they look like. Once we know what things look like, then we can start applying our transformation rules. Like, so you probably already know, looking at number 2, what x minus 5 does to the graph, what a plus 3 of the n does to the graph. So like, hopefully you know your transformations well. We just need to worry or focus on what the parent function looks like. So let's do 4 to the x first. And by the way, we're going to put all 3 of these on one graph. So if you have 3 colors, that'd be nice. If not, you can still figure it out. So 4 to the x. Let's just go -1, 0, and 1 and see if that's enough for us to figure out what's going on. If not, we'll graph some more. 4 to the -1, what's that equal to? 1 over 4. 4 to the 0 would be 1, and 4 to the 1 would be 4. So let's plot those 3 points and see what we think. Goodness, should have brought my glasses today. Small graphs here. 0, 1, and 1, 4. Okay, maybe that's enough. What would happen if we plugged in 2? That's 16, so then we're like way off the page. You can try to put it on there if you want to. Way up there. What about if we plugged in -2? 1/16. And that'd be like really hard to show on a graph so small. So I think there's clearly an asymptote, and we also go up pretty steep here. Alright, let's do 2 to the x. So I imagine it looks pretty similar because the function looks pretty similar. Let's do the same thing. Plot the points, and then we'll kind of compare and see what they look like. So 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. So let's see. Hard to tell the difference between 1/2 and 1/4 on this graph. Maybe we should do one more on this because this one will fit. 2 squared is 4. And 2 cubed is 8, so we can get cubes on there. So I think we can see that 2 to the x is not, I mean, it's steep, but it's not nearly as steep as 4 to the x. And then I'm going to do 1/3 to the x over here on the other side because I didn't plan ahead very well. What's 1/3 to the -1? 3, right? Flips it over, so then it becomes 3. 1/3 to the 0 is 1. 1/3 to the 1 is 1/3. So -1, 3. Oh, this one's kind of flipped around. 3 squared is 9, so we could get -2 on the graph as well. So there's 1/3 to the x. So it was flipped in the x direction from the others. Almost like if we had rewritten 1/3 as 3 to the -1, and this is the same thing as 3 to the -x, and maybe that's, I mean, 1/3 of the x is probably easier to think about, but if you write it as 3 to the -x, I think that helps make sense of why it's flipped, because a negative on the x flips it in the x direction. So those are the 3 key points I'm looking for on these graphs. 2 to the x minus 5. rather than actually do 2 to the x minus 5, I'm going to get my key points from 2 to the x, because it's easier. All right, because it's always 2 to the negative 1 is a half, 2 to the 0 is 1, 2 to the first is squared. But what's that minus 5 do to the graph? Yep, right 5. So it's like my new origin, if you want to phrase it that way, is right 5. So maybe overkill to put a new origin there, but maybe not. So I'll still use my key points. I'll just go from this new starting point. I'll shift them all to the right 5. So negative 1 1/2, 0 1, 1 2, 2 4, 3 8 if I want to keep going. I suppose the other way to handle the right 5 would be to actually add 5 to each x value. Sort of a numerical approach. I think I prefer the graphical approach. You know it means right 5, so just move everybody over right 5 and plot your points. Number 3. Again, with 2 to the x is our parent function. And again, if I'm doing a table of values, I'm thinking parent functions. I don't want to mess with the plus 3. Because I know how to handle the plus 3. What's the plus 3 do? Up 3. And so kind of the same thing. I can add 3 to the y values and like write out the points. Or I could just go to the graph and say, well, I can handle up 3. Let me just make my new origin at up 3 and go from there. So negative 1 1/2, 0 1, 1 2, 2 4, 3 8, 4 16 if you really want to go for it. Oops, 2 4, not 2 3. 3 is enough. I'm doing more than 3 because we're still learning, or I want to make sure my curve looks good, but 3 is enough. All right, how about a negative on the x? What's that going to do? Flip it. Let's be a little more careful, though. Flip it which way? It's going to flip it over the y-axis. I would phrase it as flip it in the x direction. The negative's on the x. So I would just say flip it in the x direction. So yes, that's over the y-axis, but to me it's easier to say it flips it in the x direction because the negative's on the x. At some point, you might just stop writing down the key points. Sort of like with parabola. When you graph a parabola, you probably don't write 1 1 2 4 3 9. You just go 1 1 2 4 3 9. Same thing here. Initially, maybe it's worth it to write them down the first 3 or 4 times, and eventually you're like, why am I writing this down again and again and again? It's always the same thing. But I'm flipped in the x direction, so let's be careful here. So I'm flipping left and right. So rather than negative 1 1/2, I'm going to go 1 comma 1/2. 0 1's in the same spot. 1 2 flipped over becomes negative 1 2. And again, you have that same option of, if you want to, you could multiply all the x's by negative 1 to get the points that you use. But I think most of you are adept enough to use just sort of the visual cues to just flip it on the fly. Ooh, e to the x. Okay, table of values. Can't use the 2 table of values anymore. I mean, it should look like 2 to the x, but what's e equal to? Here's our key point here. Or what's e as a number? Do you know? And that's close enough, right? Look how small that graph is. Like, you're not going to do any better than 2.7. So if x is negative 1, 1 over 2.7, again, like how good can you graph 1/3 on a graph that small? If we call it 1/3, that's going to be good enough. E to the 0, that's 1, so don't even need the 2.7. And then e to the first is 2.7. So it's the same stuff, it's just 2.7 is a little harder to mess with than 2. Negative 1 comma a third, 0, 1, 1 comma 2.7. And I don't think I want to do another point on this one because I don't know what e squared is. Right? Like, it's less than 9, more than 4, but I don't know it, so I'm just going to leave it alone. Again, I get my key points, I know the basic shape, that's good enough. What happens to number 6? Yes?
Thank you.
Adjust. And have your ID as well. Yeah, so that negative on there makes a x direction flip. Pardon my handwriting, x direction flip. So I've got the points over here. See them both at the same time. So negative 1, 1/3, but I flip it, x direction becomes 1 comma 1/3. 0 comma 1, if I flip that, it doesn't go anywhere. 1 comma 2.7 becomes negative 1, 2.7. So there's my x direction flip. Also notice I got lazy and didn't write down the table of values again because it's the same table of values as the original. I just have to adjust it. Speaking of adjusting, at 2 adjustments on number 7, what's the x minus 3 do? Okay, right 3 and up 5. So I'm going to do that. I'm going to move my origin right 3 and up 5. There's my sort of my new origin that I'll start from, and I'm still going to use this same table of values. So from my new origin, negative 1 comma a third, 0, 1, 1 comma 2.7. And again, this parallels with graphing any of the other parent functions. Like once you got the basic shape, now you're just moving it around. Oh, what's going on number 8? Yeah, so flip y direction and flip x direction. Okay, maybe it's just me, but I don't trust myself to like visually do that. So how could I adjust my table to accomplish both of those flips? Like what would I do to my x and y values to accomplish those flips?
Switch them.
Switch, wait, when you say switch them, switch x and y?
Flip signs.
Change the signs of x and y. So flip the y direction means I'll change the y signs. Flip the x direction means I'll flip the x signs. So not switch x and y, but switch both of their signs. So 1 comma negative 1/3, 0, negative 1, negative 1, negative 2.7. Now, if you can accomplish that without doing that, knock yourself out. I was just worried about making two flips without writing anything down. I'll try to visually make that make sense with my original. Does that make sense if I flip it in the X direction? Do that, and then flip it in the Y direction. Yes, I feel good about that answer. All right, consider page 2 here. A times B to the kx, where B and K are constant. A is a constant as well, but A is the initial value because if x equals 0, then your first value is A. So we're just kind of playing with B and K to see what happens here. If B is greater than 1, so if B is 2 or 3 or 5 or 12, whatever, then we just get bigger and bigger and bigger, growth. And so as x goes to infinity, our function is going to infinity. But if B is between 0 and 1, like if B is a half, for like the half-life formula, chemistry people, where it's exponential decay, right? Every 10 minutes you lose a half of the amount, something like that. What's the limit as x approaches infinity of this function? What's the limit of the function, right? Here's the function, here's the graph. The limit is 0. The function approaches 0, which means we can say the limit equals 0. Okay, let's see what's going on here with some examples. 2/5 to the x, 3/5 to the x, 4/5 to the x. Okay, so all of those are decreasing. 2/5 would be decreasing faster than 3/5. 4/5, that's 80%. That's not even decreasing all that much each time, but they're all decreasing. Okay, g of 3 is greater than f of 3. Let's see. We said f is decreasing the fastest. So g of 3 is bigger than f of 3. Now, if you don't want to reason through it, you just plug in 3. G of 3 is 3/5 cubed. That's kind of a yucky way to do it here. 27 over 125. F of 3 is 2/5 cubed. At least they have the same denominator, so it's easy to see that yes, 27 is bigger than 8. Statement 2. Limit as x approaches infinity if h of x equals 0. So I'm multiplying by 4/5 a bunch of times, so I'm getting smaller and smaller and smaller and smaller and smaller, and I'm headed towards 0. Right, because my base is between 0 and 1. The limit as x approaches infinity of f of x all to the -1. Okay, that's not inverse notation. Inverse notation would put it on the f. It's outside, so that's a flip thing. So if I flip it over, so 5/2 to the x. So if I multiply by 2.5 every time, what's my function doing? Getting bigger. Not 0, it's headed toward infinity. So 1 and 2 for that one. 2. The function g is given by g of x equals 81 to the x over 2. Which of the following also defines g of x? So which of these is equivalent to 81 to the x over 2? Well, I need a 9 in there. How could I rewrite 81?
9.
So I'm going to rewrite 81 as 9 squared. Leave the x over 2. And then power to a power, we multiply. So the 2's cancel. So it's the same thing as 9 to the x. That's just a little algebra gymnastics there. Why don't you try 3 and 4? Similar questions. You try 3 and 4. 4 looks a little bit weird, but if I rewrite 16 as... I could write it as 4 squared, but most of my powers have 2 on them, so I think I'd rather write it as 2 to the 4th. Wait, why does that say plus there? 2 times 2 to the 4th to the 3x. So that's 2 times 2 to the 12x. I'm pretty sure it's not B or D. What about A or C? Is it A or C?
Because it's 2 to the 1
It is 2 to the 1.
times 2 to the 12, so you just add.
And so what do you get when you add 1 and 12x? You get 1 plus 12x. So it's C. So the first trick on these is doing a substitution on the base, and then it's just some algebra, gymnastic-y kind of things. Number 5, the table of values. Table gives values of function. Which of the following could be f of x? Well, this is just like plug it in and see what works, right? Like, I'm even going to make my own table here until this doesn't work. 3 to the 0, no, 9 to the 0 is 1, plus 3 is 4, okay. 9 squared is 81, plus 3 is 84, so A's out. 3 to the 0 is 1 times 4 is 4. 3 squared is 9 times 4 is 36. So far so good. 3 to the 4th is 81. Times 4 is 243. B's looking good. I don't even want to check 6 because, ugh.
Wait, why is it 2?
You said it's 243.
Oh. Yeah, it's 3. Well, 3 to the 4th is 81. Times 4 is 324. Four times 9 to the x. I get 4 there. 9 squared is 81. Times 4 is not 36. How about that for some math?
Math is so easy.
Yeah, 81 times 4, not 36. C's out. 3 plus, this is not looking promising, but 3 plus 3 to the 0, that is 4. Okay. 3 plus 3 squared. 3 squared is 9. 12, so that's not it. It's B. We were right. Okay, 6, 7, and 8. We should have put number 5 somewhere else, because 6, 7, 8 sort of match what we were doing in 2, 3, and 4. Meaning, you're going to try to change the basis to match, because then you can answer the question. So f of x is 3 to the x. G of x is f of x over 27. Which of the following transformations of f describes the image of the graph of g? Well, f of x is 3 to the x. over 27. But 27, that's a suspicious looking number, right? Like that's 3 cubed. And what do I do with 3 to the x over 3 cubed? Okay, so now I'm looking like I can do something with transformations. So a little bit of algebra trickery there. What does x minus 3 do to the graph? Right 3. So that was a tricky one. That's weird that you would divide by 27 and end up moving it to the right 3. That seems odd. But it's because of the way the math works for exponents. Number 7 is kind of the same type thing. F of x is 5 to the x. G of x is 5 to the x times 25 to the a. That's an a, not a 9. What's 25? 5 squared. So again, once you get that first step down, then it starts to fall out pretty quickly. Like, oh, 25 is 5 squared, so that's 5 to the 2a. And then be careful here. What do I do when I'm multiplying? Add the exponents. X plus 2a. And then I just have to think about, all right, x plus 2a, that is left 2a units. So horizontal for sure. It would be by negative 2a units. They worded that a little bit weird because we're going to go left 2a. Three to the x versus 3 to the x to the negative 1. Well, what's 3 to the x to the negative 1? You could do that. I'm not going to write it that way. That is 1 over 3 to the x. I'm going to, because I'm looking at like reflections, so I kind of like to keep my minus sign because my minus sign is talking reflections. So I'd write that as 3 to the negative x. Now you're right, that is 1 over 3 to the x. But I think I like it like this because that tells me that I'm flipping in the x direction, so that's over the y-axis. Let's see what happens. So the graph of G is a reflection of f. Yeah, that's true for all of them. Over the y-axis, and represents exponential growth or exponential decay. Well, this is where Victoria flipping it over was a better choice. So like leaving it like this helps me see the flip, but writing it like that helps me see that this is growth or decay. Decay, because it's 1/3. So I'm reflecting over the y-axis and I'm decaying because of the 1/3. So I guess 2 main things today. The parent function graphs, which again you can just figure out if you forget them. You just plug in -1, 0, and 1. And then playing tricks with some substitution, recognizing powers, and then the algebra is pretty easy after that. We've already got worksheet 2. That would be today's assignment.